In the previous videos, we have discussed quite a detail about the methodology of a research. A good research starts with a good planning, which you need to structure them to be the simplest form for you to attain the objectives. Then you need to have an idea in terms of the stages of the research, and you will need to refine your planning to the data collection plan for the variables and have ideas on how you're going to deal with the analysis. You should also plan for your work schedule. It is so that you can accomplish your research within the stipulated durations for your postgraduate study. Now that you have accomplished the planning stage for your research, you will need to put everything in your methodology, which is the third chapter of your thesis, and providing the relevant descriptions, details, and specifications of all the materials, hardware, software, and the methods that you use in order to achieve your research objectives. You need to provide sufficient information for the reader to be able to repeat or replicate your words if it is necessary. These are a few examples that you can present your informations in the chapters of methodology. For a typical research, especially for the experimental study, you will need to fabricate the specimens for the testing program. Those specimens are made up of certain materials, which theoretically you need to know the specifications of those materials. You need to know what is the input so that you know what is the effect to the output. Let's say now for this research, there will be steel bars and concrete being used as the main materials to fabricate a specimen. You can acquire the specifications of the material from the supplier or the manufacturer. However, you might not be able to acquire the exact figures of the properties of the material, as the supplier or manufacturers normally provide the details and specifications in terms of the minimum quality, such as for the steel bar. Those provided by the suppliers are typically the grade of the steel bar. Let's say now the Fy equals to 500 megapascal. If you need to acquire an exact numbers for the strength of the steel bar, you will have to conduct testing on the material. Same principles applies to the concrete. Therefore, in this case, the exact numbers of the properties of the steel is important. Therefore, you need to first test the properties of the materials for both the steel bar and the concrete. We are looking at the critical specifications of the material, which in this case, your steel bar, it will be the tensile strength. You will need to conduct the tensile tests for the steel bar. The dimensions of the bar in terms of the diameter of the bar should be the same as your specimens. Theoretically, you should use the same batch of the steel that you use to fabricate the specimens, which in this case, bar diameter 16 mm was used for fabrications of the specimen. Therefore, you will need to test the Y16 bar from the same batch of the steel which you acquire from the supplier. This 600 mm long represents the sample size which you use to test the tensile test. And the property that you can acquire from the tensile test include the Young modulus, yield stress, and the ultimate stress. You need to provide the models and the brand of the testing machines that you use to conduct the tensile tests. Clearly specify the brand, model, as well as the capacity of the testing machine for the readers to have an idea how your tensile test was carried out. The capacity of the machines is very important, which the capacity in the ideal conditions, it should be slightly larger than the anticipated capacity of your samples. Let's say now you estimate the tensile capacity of Y16 steel bar having the Fy of 500 megapascal is somewhere around 135 kilonewton. You will need to choose the testing machine with a capacity at least more than 135 kilonewton. It is so that the machine can actually break the sample and acquire the tensile capacity of the sample. And it is also noted that you should not oversize the machines. Let's say now you're using a machine of 2000 kilonewton just to test a sample of 100 kilonewton, which is about 5% of the capacity of the machine. You might have some problem with the accuracy of the measurement, particularly in terms of the decimal place. The log cell built-in within the machine may not be able to give you accurate number to the intended numbers of significant figure or decimal place. Therefore, whenever you want to test a sample, you can actually roughly calculate the anticipated capacity, which in case of the steel bar, you know that the grade of the steel bar Fy equals to 500 megapascal, and you will expect that Fu is going to be about 30% to 40% higher than the Fy. Then you can estimate a maximum capacity of the sample. Then you choose an appropriate machine within your laboratory to have your anticipated capacity of the sample falling within the range of 50 to 80% of the capacity of the machines. This should be able to give you the intended significant figures for your results. Normally, we would like to have some tolerance in terms of the maximum capacity achievable by the testing machine. We barely use the machines towards 100% of its capacity. Although you know that you actually can use the machines to 100% capacity, because normally this kind of machine designed to the intended capacity have their own factor of safety. Even though the sample strength slightly exceeds the capacity of the machine will not break, only that it is not recommended in order to prevent any possible damage to the machine. Normally, we use the capacity of the machine less than 80%, especially for those machines which has service for quite a durations, which in most of the university, this kind of machine has served the university more than 10 years. You're going to expect some wear and tear within the machines, which may affect it from achieving the optimum performance towards its full capacity. These are the minor things that you might want to consider. Actually, we are not penalizing on any brand of the machines. The point here is you have limited numbers of samples, as those going to incur some cost to you, and preparing the samples require times. Testing the samples also require times. Even for simple samples, there might be quite a number of specimens to be tested. You do not like to waste your effort onto some machines that you are lacking of confidence, which at the end of the day, when you find your result contradicting from what you have expected, you start to query whether the machines contribute any of those to the variations from your expectations, or whether the machines is actually giving you the correct result, just that you made the wrong hypothesis. In order to eliminate those uncertainty, preventive measures it will be more effective. You should use the right machine in good conditions, properly calibrated, so that it yields you a good result, which indicates that the result varies from your expectations. You can omit the possibility that the machines give you wrong data. Then you might need to provide the specifications in terms of the testing conditions, which in this case is the pace rate, kilonewton per second or mm per minute. This represents the rate of force being applied onto the samples in the measurements of elongations mm per single unit. This is one of the important specifications to be provided, as you know that this pace rate may slightly affect your testing results. A faster pace rate may lead to slightly lower capacity. Therefore, normally a standard, it will limit the maximum pace rate for the tensile tests. Then you provide details regarding the numbers of specimens to be tested. If all the steel bars are from the same batch of the steel, then you only need 3 samples. But if your specimens are made of steel coming from different batches, each batch will require 3 samples. As for the result, an average value should be taken. Now you want to know the property of the concrete. You can conduct the slump test. It is meant for the workability or consistency. Then probably you need to specify how many testing that you need to conduct for each batch of concrete. And then the compressive strength of the concrete. You have to provide details of the samples of the concrete, which you can determine the compressive strength from 150 mm3 or 150 mm diameter cylinder. You know that there are also other sizes of cubes and cylinder. You need to check the standard carefully in terms of the recommended size of the sample. Normally for the concrete with the aggregate greater than 20 mm, when you want to produce the samples, it should be either the cube or cylinder of the size of 150. Although you can use smaller size, but it is generally understood that 150 mm diameter of cylinder and the size of the cube, it will give you more representative data. And then you have to be careful also the standards that you are using in your later stage of your analysis, whether you are following the Eurocode or British standard. The concrete strength as specified for the British standard, it will be on basis of the cube, and the concrete grade as specified for the Eurocode in their equations, it will be on basis of the cylinder. In the case that you are using the Eurocode, but your cube is being used to determine the compressive test, there should be a conversion to you for the result as acquired from the cube converted into the equivalent strength in the cylinder. You need the properties of the steels and concrete, especially the strength property, which in this case, it will be used to calculate the maximum capacity of the samples tested within the research program. Therefore, you will need to use the right number so that you can accurately predict the strength and capacity of the specimens. The compressive test was conducted in order to determine the compressive strength of the concrete used in the preparations of the test specimen for your research program. Clearly specify the testing machine and its model as well as the maximum capacity. Specify the pace rate, which is supposed to be in accordance to the relevant standards, and specify the numbers of specimens to be tested, which 3 units of concrete cube in this case being tested for each specimen, as you know that the concrete strength increases by each age. Let's say now you have 20 specimens to be tested. As a beam member in the laboratory, it is nearly impossible for you to test all 20 specimens within one day. Therefore, you need at least 3 cubes to represent the strength of the specimen on the day of the testing. On the same day that you test the beam specimen, 3 concrete cubes are also tested, assuming that whichever compressive strength S obtained from the concrete cube is equals to the concrete strength of that particular specimen. You know that the correlations between the concrete cube as well as the beam specimen may not be that strong, but at least they come from the same batch of the concrete being tested on the same day. The differences may be the degree of compactions and slight variations in terms of the curing method. Unless you can find a better ways to represent the strength of the beam specimen, testing the concrete cube or concrete cylinder is commonly used by the typical researcher who are testing for the concrete samples.